Hello everyone. So today we will be discussing a new paper which is titled as Evaluating Large Language Models Trained on Code. So this paper is written by OpenAI, and if you have heard of the project called as GitHub Copilot, so this is a part of that particular program, right? And they have internally codenamed it as Codex, the model which is running the GitHub Copilot program in itself, and we will be discussing that particular model. So going through the abstract, the first thing they have mentioned is they have evaluated all the metrics on a human eval so as a new evaluation matrix which they have introduced, which is more focused on functional correctness, right, rather than just comparing the solutions, right? So here what they have said is on using that particular metric human eval, they have observed that their model is about like 28.8% of the problems the model is able to solve, versus in GPT-3, the older one, it was able to solve around 0%, and GPT-J around 11.4%. So GPT-3 model, as many of you might know, is a very popular commercial service also, which is in beta. So there the intention was never to create a model which could write code and provide solutions, but still as a byproduct of language training, it happens to understand the code pretty well, and it is able to write out and present correct code for some particular problem statements that they have, right? Okay, so let's go a little bit down. So they have just explained what I have mentioned over here in this particular line. Before understanding this particular graph, I would like to just walk through what this evaluation framework is that we are discussing over here. So evaluation framework, the human eval framework that they are calling it as. So originally in many of the research papers you might have seen this BLU score being referred. This BLU score is very good in terms of language translation, or is intended for that kind of metrics, that kind of solution, and what the metric might be. So but this is not very accurate when we try to use it for different kind of things. Like in this scenario, we have some code, but we know that this code is working fine for all our unit tests, right? Versus the BLU score, which may be saying otherwise, right? So this paper is just trying to elaborate on that, this particular section, that why BLU score is not ideal for checking out whether our model is correct or not, right? And they have just justified that with a few examples, and instead they are suggesting a different approach here, which is they are saying there is a metric called as pass@k metric, the human eval metric, where if you take n as the total number of samples here, and c is the number of correct samples, and k is in the correctly identified, the accurate number of samples which have passed all the unit tests, right? So let's say if I say something like pass@1, right, versus pass@100, what it means is that there is one code sample solution which is generated by our model, which we are taking into the consideration, which has passed all the unit tests that we have provided, right? That's what the pass@1 is mentioned. And pass@100 is we have taken 100 different solutions which have passed all the unit tests that we have provided it, right? So these are two different matrix bifurcation that we are taking into consideration for our research paper, right? So now following up on that, I'll just quickly go and discuss this particular one. So here they have said they have taken n equal to 200 and k is less than equal to 100, right? That's the upper limit that they have taken, and the n is the total number of samples that they have taken, right, per example, per problem statement, right? For BLU score, just as a reference, I'll just reiterate as like BLU score. Let's say if it is 0, and versus if it is 1. So if it is 1, then the solution that the model has provided is of an exact match, right? And versus if it is a 0, then it is not an accurate match, right? It has failed whatever intention was behind matching was there, right? So that's just a quick reminder of how BLU score works, right? We'll just go through the human eval part first. So here, while creating the data set overall, we are basically focusing on different kind of data sets. One of the data set is the APPS data set. This data set is basically the code forces repos, containing solutions to code forces problems. What is code forces? Code forces is a competitive programming platform which a lot of coders use to participate in and win prizes, right? So they have taken a lot of problem statements from there and they have provided solutions for that, right? So this is more of a competitive programming from a competitive programming standpoint, right? And they have taken this data set while building out their solution. The sandbox environment, or what kind of environment they are treating for running or training this model, this is a container. Okay, so it's like a Docker container, but it's more like a gvisor container runtime, right? They have suggested that because the code which is present on GitHub, which they are taking into consideration, may contain malicious code and that may harm the host system, right? So that's why they are not just dumping it on any server. They are using this particular gvisor runtime so that they have a contained environment in case if there is any sort of malicious code that is present while training the model itself, right? So this, I hope this part is clear. And gvisor protects by differentiating its host and its containers, right? So there is a security boundary over there. I won't go into too much depth, but just as an understanding why Docker is not chosen. So this is the reason for that, the security reason, all right? And it is done on Kubernetes, the container orchestration platform, and it is run on Azure. It's written in the paper as well. Okay, so this part is good. Let's move on to some of the other aspects of while training the model, right? So just as a reminder, they have told us that, okay, when you are evaluating one evaluation per problem, like that's the budget that they have in mind, like, generally budget is not a correct term to be, used here, but just for reference, like they are sticking with one evaluation per problem, right? They are somewhat like using as like pass at the rate 1, right? Which one solution which has passed all the unit tests. There may be other types of solution, but they are not considering it, and they are just considering while considering this one solution, which solution to pick up. Whatever has the highest mean log probability, right? So that's what they are picking it up, right? The solution which they are picking up, right? Okay, for the data collection part, so our primary language that we will be training our model is for Python, right? And they have a data set of around 179 GB of unique Python files under 1 MB, and the final data set they have trimmed it down to around 159 GB, right? So what kind of trimming can happen is a bit of like white spaces that they have mentioned, right? Let's say there is a lot of white spaces happening in the code, so they have removed those white spaces, and that's why they are able to reduce the amount of data size. And it is a good practice to do that so that you don't confuse the model or improve the training of the model in itself, right? Improve its accuracy, right? So that's a good way to do that. Another way is like they have introduced stop sequences. So let's say if there is a /n class or /n def, right? There's a new line at each of these terms, right? So what you can do is you can just treat it as a stop sequence, and you can make the model understand that, okay, this was a different part of the problem and this is a different solution that the particular Python file may have, right? So these are few of the things that they have done. Another like hyperparameters and other stuff, what they have taken is they have taken ADAM optimizer, beta 1, beta 2, and there is epsilon also, right? Weight decay coefficient. So these things are just as a hyperparameters we are treating. Okay, now let's just go to the results. So what they have observed is as you scale the model in itself, right, starting from less number of parameters to a large number of parameters and large data set as well, you tend to see that it is able to scale efficiently, right, at a given correct temperature, right? So what's the temperature? So I have just taken some references over here. So temperature is nothing but it's a randomness in the output. So let's say if the model predicts or is about to predict, let's say how to make, something like that, and you have the model prompt more number of words going forward, right, to complete the sentence, right? And if you choose temperature as 0, right, so what it will do, it will give you this output, a good impression on a first state, right? So what it means is model has like multiple options, right? So when you set the temperature as 0, it is basically picking out the highest mean log probability, right? And it is giving you the output for that. The good thing about it is like it's the most stable answer that the model thinks it is there, right? And if you set it as temperature equal to 1, which is just the reverse, it will start throwing out a little bit more gibberish kind of words like turban wrapped, coconut hairdo, mayo without almost no oil at all. So stuff like that, right? So any kind of thing that doesn't really make sense, even it will try to throw it into that, right? So mean log probability is the metric which we try to identify which is the most correct sentence here, to complete it, and then we test it with that, right? So just a quick word on log probability. Log probability is nothing but taking the logarithmic of a probability. I think the most simple reason why we do that is basically computers are really good at addition, right? And when you try to have multiple probabilities, basically you have to multiply each of those probability to get the final output, right? And instead of that, what you can do, you can take the logarithmic of it and then you can sum it all up, and because the computers are really good at adding it up then multiplying, so you will get a faster computation while doing that, right? So that's just a good quick overview of why and what the temperature is and the mean log probability part of it, right? So here, if you see here, they are just saying that, okay, if you have something like pass at the rate k, like one sample versus just a number of samples, you will see that as the the number of samples are increasing, the pass at the rate k part is also increasing for particularly, I'll just delete this part. Yeah, so basically it is increasing for this yellow line, which is the pink line, which is the t equal to 1.2. so this line which we are discussing, it's going way beyond what is expected, and it is increasing as the number of samples are increasing, even at the pass at the rate k value is also increasing, right? So different temperatures have different curves, right, where how much it is able to scale. So we get some idea that, okay, as the temperature is increasing, the curve is increasing, the number of samples is also increasing, so we are good. It means that if the model is at a higher temperature, or just a reverse, if the model is having huge number of data sets or large number of samples, then it will require a higher number of temperatures to perform well, right? So just a quick summary of what that curves and graph represent, right? Now going over to the best temperature versus k. Okay, so they are trying to identify some sort of best temperature, but as you can see, it's like a step function graph over here, and the best temperature is like 0.8 over here versus 10 to the power of 2. So as the number of samples are increasing, the temperature is again increasing. So it's just a quick summary of that, okay, the number of samples and the temperature is increasing, right? Okay, the model size is also quite okay, because the pass at the rate one is we are just picking up 1 versus 100 samples which have passed all our unit tests. So if we pick it up at 100 different samples at 0.8, you can see that the orange line is quite high over here, and it is increasing with the number of parameters as the temperature is also increasing, and the particular number of sample that we have is also increasing, right? So it is quite good, and for one it is a little bit low. So this is just basically to justify that our model is able to scale well if we have large number of parameters, and if the temperature is somewhat increased, right? To, let's say, instead of 1 you take 100, right? Just as an example. Okay, so let's go over a few more things. So here they are just taking BLU score into consideration, and they are just comparing it with the human eval matrix, and they are just justifying why BLU score is not equivalent to optimizing like the functional correctness, right? Why is it not a correct metric for that, right? So it's quite clear with these graphs that it is not a correct metric to justify over here, and when they compare it with some tab 9, which is a competitor to what they are trying to achieve, they have just shown some metrics around that, right? Which is like 2.6% pass at the rate 1 versus 7.6 pass at the rate 100, right? At those temperatures which the model is performing, right? Okay, seems quite decent the way how they are approaching this. So here just a quick update is like we are taking not just the main model itself for the codex, we have a few different models with different parameters, right? So for codex itself, if you see here, they have taken a lot of different input size or the data set size, like 12 million versus 12 billion, right? And even for GPT-3, right, there is GPT Neo, there is GPT-J, right? So different kind of accuracies are obtained for different kind of samples that they have, and different kind of temperatures, right? So it's just that the accuracy is increasing with the higher the number of parameters here, and even in both scenarios, right? If we take one sample versus 100 samples, both of these things are increasing, right? If you see, right, I've just highlighted it, right? So it is a good indication that the model will outperform because of the data set size, right? So if we increase the number of data set, the size of the data set, then it will outperform the existing ones, right? So that's just what the approach they have taken and what they have discussed over here. Few things that they have discussed over here is the coding interviews one. So in GitHub, right, we don't have that much code which is more technically like a coding interview problem, right, where you have input, you have output, and then you have some sort of example as well, right? So you don't have a lot of data sets in that way, or a lot of code in that way on GitHub. So that is one of the reasons why they say that even in APPS data set, the only thing is this is something that is different than the GitHub data set, right? So they have used that, but the accuracy of that is not very good. Like in the later paper, they have shown, I will scroll a little bit below. So they actually tried passing, okay, I'll come back later. So they actually have tried passing coding problems, right, to the model, and there is a graph somewhere down that reflects that okay, the model is not able to perform very well on those coding problems. So that's just a way to represent that at the moment this model is not very good with the coding interviews and the competitive programming kind of a scenario or those kind of problem statements, right? Okay, so one model that is particularly interesting is with the CodexS, right? Your normal codex is there, and then there is something called as CodexS. What is CodexS? It is inclusive of the competitive programming aspect of it, right, along with the CI/CD tools which GitHub uses, like most famously Travis CI and the Tox one, right? So we will see how this model perform with the existing codex model, and how it may be improved, right, without a lot of changes, right? Okay, so let's go down. Okay, so here is the table. So if you see here the introductory, interview, and the competition, right? So the accuracy is quite low, right? If you have one shot codex, right, you see that it's only like 20% accurate, right, for introductory, 3% accurate for interview, and 3.23% accurate for competition, and this is for 1000 samples, right? So these metrics are not very good when you see coders solving competitive programming, right? So that's just the result of the paper that we have just we are just discussing that part over here. So our model is very good with introductory, which means like basic introductory level kind of problem statement. So that thing is there, but otherwise you can see that it is not very good in terms of the competitive problem statements, right? So yeah, so that's what it is. They have just discussed on the left side this tracing part, why tracing is necessary, and because our model, another thing is like our model does not need to know advanced algorithms and data structure. Now why is that scenario over here? So just try to understand it, like the authors have chosen a pattern matching based approach over here, rather than trying to make things more understandable for the model. They are not basically educating the model to know what is a trie data structure or what is a binary search and stuff like that, right? The data structure in algorithms like we used to understand, right? Like humans have to understand that. They are just training the model and giving them examples, and the model is figuring out what makes sense and what doesn't make sense, right? So it's a more like a pattern based matching sort of logic over here. And yeah, that's what the justification is, that why tracing and all these things may work and why it is needed, why it is not needed. There can be different ways also to approach this particular problem. Like in one of my previous papers, the Facebook authors have tried to make the data set using trees, right? So that approach is also good because it's a symbolic approach, but again the authors have chosen a pattern matching based approach for this particular one, right? So questions about quality, right? Why quality is of concern, right? Let's say even if you have 100 samples per curated problem, right? But how many are really good, right? So what is the method that they are using to evaluate that? So as I discussed, the method is the log probability one, right? But more a little bit on that is, let's say if you are using some sort of a prompt, right? You are not exactly trying to solve the problem or expecting the model to solve the problem from an end-to-end perspective. You started somewhere and you are expecting the model to complete like this part, right? So in that scenario, basically a prompt, we need to do some padding, right? Padding is required to find out like the tokens length, right? So that let's say if you have a prompt which is very huge versus which is very less, so how is our model doing in that scenario, right? Is it actually able to figure out long prompts, or is it only good with short prompts? Like what is the scenario? So they have done some sort of padding over here, but overall in a rough overview kind of a sense, they have shared that when you have a long prompt, the model is not able to perform very good. Shortest prompt is much better, right? Find that CodexS is prefers slightly higher temperature. So this is quite okay, because we know that S is trained for larger data sets and has higher temperatures, right? So this kind of thing is quite okay. And if this is again the same point, that CodexS has higher temperature, so it is performing really well, right? So this is a pass rate versus model size. So pass at the rate 1, pass at the rate 2. So just comparing the Codex versus CodexS. So CodexS is outperforming the Codex model in both the aspects, the at the rate 1, at the rate 100, which is like 1 sample versus 100 sample. And this is just a representation of that particular thing. There is something called as CodexD also, which they have created a model. So CodexD is a docstring model, right? So basically you have a docstring like something like this definition, and you expect the model to understand the docstring and then create the code for it, right? So this is again a different type of technique over here, and then we are just evaluating on that, right? Okay, CodexD issues, what they have encountered is it leaves important details over conditions the function name, right? So these are some minor issues that they have observed. So I'm not sure how GitHub Copilot is working, let's say, because ultimately I believe it's one API only, which they have commercialized and working with. But I assume that if there are different models, maybe different models are working for different things and then combining into one single API, and I don't know how that commercialization is done in that way, right? But it looks like this kind of research is there. Instead of having one model doing everything, they have different models for different aspects for it, right? Okay, so this sounds good. Okay, just overfitting problem that they have described over here. They have defined the accuracy levels, which if you see here, Codex S is doing much better over here with 32%, 59%, right? And this is in both aspects, at the rate 1, at the rate 10, right? 1 sample and 10 samples, right? So it's quite good. Okay, some limitations we will discuss. So Codex is not not sample efficient to train. Okay, which means like it is not a efficient way. What we, let's say you have 12 billion parameters, right? And the Codex is performing, but it is not performing as good as what the expectation is, right? So that's just one of the issues that they have taken, right? Okay, another thing is Codex calls functions not present in Codex. Okay. Okay, so yeah, this is another issue. So one of the issues is, let's say the model Codex has presented some output, right? And that output is moreover like correct to the human eye in the first glance, but when you actually run it, it is not correct, right? One quick example is this one, right? Here the authors have given some docstring like add 3 to y, then subtract 4 from both x and w, return the product of the 4 numbers, right? So t is equal to y plus 3, which is correct, the first statement. Subtract 4 from both x and w. So x it did 4, but w it did not do. Okay, so it just followed on and it did the product of the 4 numbers and it gave here. So this is not a correct output that was expected, right, from this model, right? So this is just a way to say that the model is not entirely perfect. It is still an issue with its work. Security risk is always there. Let's say if the model generates some sort of security risk with the code itself, right? It is trying to break or misuse some sort of safety challenge that already exists, right? So then it's a misuse, right? So that's just a thought over there. Over reliance, misalignment. So yeah, I mean, if you rely too much on Codex and you just don't check what it is doing, then it's a issue, right? So as I have shown earlier also, like it is producing code, but it is not accurate, right? So that kind of issues can happen. Auto completing code which has subtle bugs. So okay, bugs can happen all the time, right? That the code it produces has bugs, right? We have seen that. Bias can be there, right? Let's say if there is some code which is bias in this scenario is, let's say if a lot of people are using Flask, and you have import Flask a lot in the code, but there is something called as fast I think API, right? So that kind of framework is also good, or some different new framework comes along the way and which is much more efficient, but due to the data set it is not picking that up, it is preferring Flask, right? So that is a bias, right, towards a particular set of library, right? So it's a quick thought on that, right? Again, the same is repeated over here, and open source will have some corrupt data as well. It may do wrong things which are not correct, right? So that's another issue. So just these things are there which they have highlighted in terms of what can be legalized and what is the risk part of it, right? So I won't go too much into depth because there's just a theoretical overview of it, and yeah, I mean this is some related work which they have highlighted in terms of the NLP, and how, as I was also discussing earlier, like ASTs could be used right, for some sort of tree structure basically to generate this kind of model and help it better understand the code part of it. So few examples they have given. Even T5 model, someone have worked on that, right, to train a T5 model with Python 1, and using beam search also it is possible. So there are different techniques to do that, but it's just a rough overview of it. Okay, so this is it, the conclusion and everything. They have given quite good the estimation and other derivations and theory part of it. They've given a lot of good samples of what is happening over here, right, and you can go through it. I think it's quite useful when you are understanding it, and they've given some building blocks for synthetic tasks, because a lot of the problems which they have come up here in this particular one, it is handwritten problem statements. It's not exactly like copy paste from the lead code or something, right? So they have taken some time and effort to put together these problems and test framework for it, right? So this is it, I think. That's it. And I will leave a few referral links in the description, so feel free to go through it. And that's it for this one. It's a very interesting paper, and I really like this kind of approach, and hope in future we'll see more better approaches than the current one, right? Okay, so thank you very much. See you. Bye.